This is Milkish Inlet #1 bridge here, Bayswater, built in 1920. This bridge, as you can see here, the 4.2 meter height and 5-ton restriction, had been in service for 100 years in the community. And the province had decided that the community needed to have the bridge upgraded from 5 tons, as you see here, to 30 tons, so that emergency vehicles, snow plows, school buses, all could cross the bridge and not have to reroute around it. And that's an important feature for service in the community. The bridge had been designed originally for 12 tons. Back in the day, the heaviest thing was a Model T Ford, or a heavily loaded wheel cart pulled by horse. And the designers back in the day had designed this howe truss covered with sidewalls and a roof, had designed it to be protected from the elements so that its connectors wouldn't get moistened with higher moisture contents decay. And so it was all wood, all the joinery was wood with some cast iron pins and nodes that were in it, but basically all timber. And this howe truss had served the community here for 100 years. So what was involved from an engineering point of view in terms of being able to increase the capacity of this bridge, restore degraded elements, and to be able to extend its life another 100 years with a much higher load capacity than it had ever been designed for to begin with? Well, the first part of it was to find the bad actors, use non-destructive testing like through compression wave analysis to find where the reds and yellows, that's where the degraded elements were, either fully degraded or partially degraded. Then assess their in situ capacity, assess the bridge's capacity to serve the community with 5 tons, 12 tons, or 30 tons by modeling the bridge. And so what we did was inspect it, determine the degraded elements, their location, then model that bridge's capacity and find where the deficiencies were. And go in with our design and restore the deficiencies, upgrade them with pieces of retrocom in the compression side, or shear panel where it was shear failed, or tension fiber where it needed more tension capacity. So the design then involved raising up the bridge and restoring camber. So we built an assembled reinforced glulam girder lift system, rolled it onto the bridge, put rods down through the deck, used those rods to basically lift the whole bridge up 75 to 80 millimeters, its original camber. Once in the raised condition, then we changed out elements and restored elements and used high strength fiber to restore the bottom of the tension cords and increase their capacity. And this high strength fiber was 5 times the strength of steel at 1/5 the dead weight, and it was adhered to the bottom of the tension cord integrally so that plane sections remained plane. And this piece then would be able to carry the full loads from a 30-ton vehicle. Once this was completed, then the lift system was disengaged and the bridge was allowed to take its dead weight. And when we trialed the proof loaded, we called it, we proof loaded the bridge using a 27-ton gross vehicle weight truck filled with gravel, and it was weighed at the scales, and then we positioned the truck at various points across the bridge, and we drove it across the bridge at 25 kpms to simulate dynamic traffic and measured deflections and the response of the bridge to load. In addition to that, we used strain gauges. These strain gauges were placed on elements within the bridge, the compression cords, the tension cords, the floor beams. And these strain gauges are wirelessly connected to a hub, and that hub is wirelessly connected to the internet, and these numbers for the strain on the bridge are fed directly back to the WRD office where they can be monitored every hour, every minute, every day. And that allows us to take the traffic counts, it allows us to check how heavy the loads are that are going across it, and to see the condition of the element over time as it continues to carry traffic. And that's an exciting way to take a 100-year-old bridge and use today's current technology to reinforce it, today's current technology to understand its response to load, and today's current technology to monitor its health downstream. Because we're interested in its health. It's a 100-year-old bridge, and we're restored it to go another 100 at basically 6 times its plated capacity of 5 tons. So when you do that, it's important to protect the community and the public And the use of these ongoing health monitoring systems allow us to do that. So the story in summary is that we have the carbon-friendly timber bridge, the sequestering carbon, having its life extended, its capacity increased, using advanced technologies to continue to restore the best service for the community, the whole time protecting the aesthetics of the community. Inside this bridge, carved onto elements of the bridge, are the initials of the community from 1920s and 1930s, where lovers met to kiss one another and introduce one another together and got engaged together and talked about their love stories together. And that story in the community of these people that crossed the bridge and used it and left messages carved into the bridge, that story is preserved to continue to carry the right kind of loads and extend the life of the bridge the right way for the community. A story to be told for sure, from not only the aesthetics, carbon, and community point of view, but from the engineering point of view too. Thank you.